Hello, the Darkness344 here, and today in this video we are going to be doing the long-awaited ALU tutorial. And basically all this video will focus on is building the actual ALU itself, showing off what it can do, as well as programming it. I may also do another video in the future detailing like how to do conditional branching on the ALU, which would be stuff like lesser than, greater than, if ALU is equal than, for the input, both inputs, if one input is lesser than the other, or that might come in a future video if I can, if I would do that. But yeah, so well, let's just get started. So in this first part of the video, I'm going to talk about like all the different things it can do, and the second part I'll actually just be building it. There should probably be timestamps on this video. I don't actually really know. But if not, sorry about that. But yeah. So, alright, let's get into the video. So, first of all, we have these different things over here. And this first section, which I'm doing right now, will basically show what each of these bits do. So, first of all, let's start at the very start of the ALU and work our way down. So, as you can see, this ALU is quite a small. It's not super small, but it can do most functions. The only functions it cannot do, as far as I'm aware, are shift left and shift right. And that's just because, well, you can technically do one of them by just putting the same number in twice. But the other one you'll need to make like a dedicated module like this, which, so I put in this number, I can shift it left or shift it right, as you can see. However, this will be in a different video tutorial I'll show you off. So, the functions this can do, I have a little board over here. So these are all the functions, the basic functions you'll be able to do with this video. Of course, you'll be able to do any of the inverted versions of these, so you could do a NOR instead of an OR if you wanted to, or a NAND, or whatever. But these are the basic functions. You have AND, OR, NOT, and XOR as the basic logical gate functions. And you also have sum of the inputs, and you can also use subtraction. And the way we'll program that, we'll use 2's complement as... you could, of course, program 1's complement to do it for the method of subtraction, but 2's complement is much better, typically for this sort of thing, for dealing with negative numbers especially. And of course, we're going to have a carry in and a carry out flag over here. So yeah, let's just show you off what it can do. So of course, this ALU actually includes registers, as in most of my ALUs always include registers at the start of it. And this is basically so the ALU can store temporary numbers in the first set of registers or the second set of registers. So A and B just stand for first number or second number, basically. And that's how these work. Then of course over here you can invert either of them. You have an AND trigger, you have carry in, you have cut carry, which is quite useful. You have the cut adders, so this will basically bypass the entire adders. So funny thing about this over here, right? I actually recorded all of this tutorial over here, as you can see. I recorded the whole tutorial on this ALU over here. As you can see, it's slightly different. That's because I completely forgot to add the cut adders. And also, I built it so it's one block too high over here. It doesn't matter, but it just doesn't look that nice. And yeah, I just got kind of annoyed because I spent, I think over an hour, maybe an hour and a half worth of video anyway. Probably more like 6 hours real time doing takes and recording it all. Just building that, it was not fun. I'm kind of disappointed. But yeah, it's all fixed with this new design that I've designed. As you can see, these are the previous iterations. And thanks to Bedrock and its weird redstone features like glass not powering this piston, it actually works quite easily without very little changes to it. And so we have our cut adders right here. Which, well, technically it's bypass the XOR gate, bypass adders or whatever, but I'll just call it cut adders because it makes more sense. Then we also have invert output over here. So you can just invert the output if you want. Let me just get rid of this. And of course, we just have an ALU outline. You don't actually need this. This is just the way I normally make my computers. Is I make it so on one clock cycle, you put in a number to the first register. On the second clock cycle, you put in a number to the second register. And on the third clock cycle, you do your operation as well as read the ALU, as well as input it into a RAM location. So it does several things at once in the third clock cycle, meaning that to complete a total operation in this ALU only takes 3 clock cycles, which is quite efficient. Of course, there's ALUs out there which are much more efficient and much more smaller. This is quite a big ALU. It's only 4 bits, this one. Of course, it's infinitely expandable even. However, as you can see, it's quite large compared to, say, look at this design over here. And it's also ripple carry adders, which make it kind of slow, but it's still fast enough to work in most computers anyway. As you can see, this ALU over here, which consists from here to here, is around the same size. Oh wait, but it's 8 bits. This one is by Nubosaurus, I think, and I've slightly tweaked it to make it a bit like 1 block smaller, but it's pretty much the same thing. But yeah, as you can see, it's a bit smaller, but it's more complex. And this one I just wanted to show you because it has all the features and it's quite nicely laid out for quite a simple tutorial. It looks complex, but it's very easy to understand once I go through it. So with that, let's actually begin the tutorial. So one thing to note before we start building is that the way I've designed this, of course it can be swapped around when you build it, but the least significant bit is on the left and the most significant bit is on the right. That means this will be the side that starts with 1, so 1, 2, 4, and 8, and this will be like the most significant one. Of course, this is infinitely expandable. However, if you wanted this side to be the one that starts with 1, so 1, 2, 4, and 8, there's several things you might have to do, like you'd have to just swap the half adders the other way around. So instead of it going this way like that, you'd have to have this signal going into this one instead, and the carries, instead of coming from here and going into there, we're going to want them coming from here and going into there instead. So hopefully if you know about least significant and most significant bits, I think Nubosaurus did a video on that, but yeah, that's how you do it. Sorry, I can't really show you, I just don't really have too much recording time left. But so the first thing we're going to do to actually build this is we're going to block up a bit, so like this one over here, the failed attempt, and this will be just where we start. And what we're going to want to do is we're going to go out like 3 blocks like this and place a lever like this, and this will be our first input. And then we're going to repeat this 3 more times because we're building a 4-bit ALU in this tutorial, because I'd say 2 bits is just a bit too small. Even though it shows the tileability, it's just a bit too small for just to show how it works. 3 bits is just an odd number, and 4 bits is just fine for something like this. So here we go. So these are all our inputs, and we're going to go down like this, and let's just label them for now. So this will be 1, 2, 4, and 8. And one thing to bear in note, normally the way I've designed I'm using D flip-flops as the registers. And the problem is they have feedback like this going down. Normally you'd need repeaters, but we're going to want to make this as fast as possible, even though it's kind of slow. So we're going to be using slabs instead. Make sure you're using slabs and not glass, because yeah, just to reiterate, this is Bedrock only, because we're going to be using glass and slabs in the design. But the reason for this is, let's just make a little demonstration here, like this, and if we do the same again over here, glass and redstone, like that. as you can see, technically glass and slabs are both not solid blocks. So what that means is if you pass a repeater through it, as you can see, a solid block will pass a signal, where a non-solid block will not pass a signal, and even if I do a top repeater like that, it won't pass a signal. And the same with glass. And some of these non-solid blocks have certain properties, like the slab acts as a diode. As you can see, you can have redstone going up like that, but redstone cannot travel down like that, so it can function as technically a zero-tick repeater, which is quite useful. Of course it won't repeat the range, but if you wanted it to only act one way, where as a repeater you can't, as you can see it won't go this way, you can use slabs instead. However, glass, on Java Edition, it acts the same as slabs as far as I'm aware. On Bedrock Edition, oh wait, it flows downwards as well. This is, however, quite useful, as you can make towers like this, where you can't on Java Edition. As you can see, redstone can flow downwards as well as upwards, which is quite useful in certain things. I've used them in certain computers before. But yeah, this was just a long demonstration on the reason why we're going to be using slabs and not glass. So now let's actually continue this tutorial before I get even more sidetracked. So what we're going to do is go up like this with some blocks, and we're going to place a slab like this, and these were just blocks to do that. And then we're going to block along like this across all of these, and we'll just break these ones over here like this because they weren't needed, and then we'll place redstone dust on top like this. So as you can see, redstone can travel up, but redstone cannot travel down. So then we're going to bring out blocks like this, and once we've done that, place another block here, block up like that, another block up like this, block here like that, and 2 blocks like that. And then we're just going to put redstone down like this, and we're going to repeat this on all of these again. So just bring it up like this, and then across like this. And this is just the base, the main bit of the D flip-flop we're making, because we're using them for registers. And once we've done this, then we can place redstone on these bits over here, redstone on these bits as well. However, we're not going to join them up like you might see on D flip-flop videos where I use D flip-flops. I place repeaters here on 1 tick. Instead of joining them up, I'll show you what we're going to do to control them. The reason we don't join them is because they're 2 different locations. So this is location A and this is location B. So if you join them up, you'll be doing both locations at once, and we don't want that at all. So now that we've done this, we're going to actually add the rest of the circuits. So redstone torch like this, here and here. So block over here and over here. And we'll just repeat this on all of them like this. Oops, make sure they're on 1 tick. So now once we've done this, we're going to want to block over here like this, block down like that, redstone dust on top, so this torch is going into that, block up like this, and redstone torch here. Then what you can do is place a block off of that and redstone torch, so we can just go down like this. It makes things a bit easier. And we'll just do this for each of them until we reach the end. Now we're going to want to do the redstone line on all of them, so I'll just bring blocks all the way to the end like this, redstone on top like this, so right under these, so this torch goes into redstone, which goes into this torch. We'll just make sure to do it on all of them. Then we can break these blocks in the center here because we don't actually need them, they're just kind of sacrificial blocks. And now we've got almost our D flip-flop. So the last thing we want to do is place redstone torches like this. And as you can see, if we didn't use the repeaters, the line would go into the other flip-flop, and that is not what we want. So now that we've done this, these torches are our output, these are our inputs, and these are our control wires. So the way we're going to do the control wires is block up like this, and here. And the way I placed a block on top of this without doing anything. When you're flying, if you just hold shift, you'll go down like that. So to fly crouch, if you hold shift and space, you'll just stay stationary in the air like that. So that's what I'm going to do for that. Then we're going to extend the wires along like this. And we're going to just do it all the way to the end over here. And we're going to place redstone dust along all of these like this. And we'll place torches on these now. So over here, this one is going to be register A, and this one is going to be register B, like that. And we're going to need to invert these because we're going to be placing torches down again. And so also inverting also shows how far our signal reaches and if we need repeaters or not. And I'll show you how to add the repeaters in once we get the torches. So since this is going to be our registers A, and this is our A, basically, register, and this is our B, it goes A, B, A, B, A, B, etc. We're going to want to place redstone torches on all the ones which are going to be A. So since this is A, redstone torch, that's B, we don't put torch, A, torch, A, torch, torch, and we're going to do the same for B on the B one. So you don't want to place it on A, you're going to want to place it on B, like this. So now that we've done these, make sure if these aren't on, so these torches are on, so these lines are on, and make sure all these torches are turned off so the signal strength reaches them. If you need to place repeaters, make sure you do not do it on top of the torch, because say I place a repeater on top of the torch will not be activated. Whereas if I place a repeater behind the torch, as you can see, it will be activated. So that's where you're going to want to place repeaters. You can just place them behind the torch anywhere. So that's the registers done, and yeah, ready to move on to the next part. Now we're going to build the inverters for this, and the way we do this is quite simple. I can't remember who made this inverter design, but it's a very simple one, and let me just show it real quick. It's basically like this, block up like that, and this is our output over here. And as you can see, we can put a line in like this, and as you can see, it will normally let signal through like that, but if we choose to invert it, as you can see, the signal gets inverted basically. So that's what we're going to be building now, and we're going to be making it for both registers B and A, so you can invert either one. And the reason we do it for both is because it means you have more options for your ALU, like subtraction. So for like, if you want to do A minus B or you want to do B minus A, it just adds more options. That's the reason we're doing it for both. So the first of all we're going to start is over here. So these are the torches from the registers, and we're going to want to take an input from this. So the way we can do this is go down like that, and if we go up like this, a block up like that from that one, redstone torch, and block here. As you can see, don't worry about this being right over here. This redstone torch does not interfere with this line at all. So we're just going to repeat this for all of them. And actually, before I do that, I'll just make the rest of the design. So the way we're going to do this is block down from that, repeater, block on top of that repeater, make sure they're only on one tick, repeater there, block up like this. Yeah, this will not interfere with this, so don't worry. Block up, dust, block up, dust, and then if we'll just go a few blocks up like this, piston, and there we go. So whenever I activate this piston, it will invert it. So now we're going to repeat this for all of them, and the way we do this, we're just going to go like this. It just makes things a bit easier, and then we can just break every other one. There we go. And then we'll just do the same for all of these, and I just go up like this. Take these ones out like that, and then of course the repeaters in between on one tick, and just these blocks we can get rid of too. Yeah, technically you can leave them in, but it just makes it a bit nicer, removing unnecessary things. It's better on all your designs to only have the necessary things you need. If you have any like extra blocks and stuff in between, it may either interfere with your design, or it might not make it look as nice. Or it's just, if you're flying through trying to debug it, you just have blocks in the way. So it's just really good practice to make sure the only blocks or anything in your design are stuff you actually are using. So all my designs, I won't have like extra blocks or anything, I just try and take them out, just to make things a bit more simple. Then we're going to have blocks on top of these repeaters, blocks off of this as well, no redstone dust on top, make sure. Repeaters like this on one tick. Oh wait, no, not over here, on the one on top, like here. Because these ones we're going to have redstone dust on. And we're going to have blocks up, oops, like this. And then we'll also have dust on top of these, and then we can just extend this piston line over here like this. I'm just going to go like this. And of course these are still separate ones, but I'll show you how to separate this piston line out. Because if we activate this piston line, it's going to activate both of them, but we want to separate it out. And instead of doing the thing that uses up a lot of space like this, there's a much easier way that, because of Bedrock, you can do. I think Java Edition can do this way as well, but this ALU tutorial is only for Bedrock Edition, unfortunately, just because of some of the things I've used to make it a bit smaller. So now that we've done this, the next part we're going to do is we're going to run a line down across like this, and a line down across like this. We also have to remember to place all the blocks underneath like this, so make sure each of these pistons has a solid block underneath like this. I just use white concrete, but if you use like cobblestone, or I don't know, you could use most solid blocks. Just make sure you use a solid block. Then what we're going to want to do is we'll just take these middle ones out between. I didn't need that lever, so I removed it. And then we'll just do the same thing here. So this one on the right will be A, and this one on the left will be B. BB. Just add the signs. Invert A. Invert B. Levers like this, and we'll have redstone running down like this. However, this still activates both of them. So the way we're going to fix this is, on every one that we don't want activated, we're going to break and place a block of glass like this. So if we break this, so since these are the B's, so A, we want a block here, B, we don't. A, we want a block, B, we don't. And we'll do that for all the A's and all the B's like this. Wait, have I done it wrong? I think I've done it. Oh no, I've done it correct. For this, of course, we don't actually need these blocks. But since we want to be able to tile it, we'll just leave them in there. So then we're going to want to run redstone across like that. And of course, we'll do the opposite thing for the B's as well. I don't know what happened there. I think my game is kind of lagging because I got it on experimental mode. And I also have that massive thing of redstone over there, which isn't exactly helping. But yeah, so now that we've done all of these, as you can see, if we activate invert A, only the A ones will activate. As you can see, since our input is all zeros, we should only have one like this. This is perfect. And if we do it on B, only the B's should activate. As you can see, the last one doesn't activate. That's because it's run out of signal strength over here. But we can easily fix this by placing a repeater down like that. And since, of course, if we wanted to tile this, we're going to want to do it on A as well. We'll place a repeater. Make sure the repeaters are not next to the piston like this, or the piston will not activate. So just the same thing with the torches. If you're placing repeaters down, make sure it's not on top of the torch. Make sure it's either in front of or behind the piston. And so there we go. Of course, if you're doing it on the A side, you can place repeaters on top of these glass blocks if you want, but make sure not to place them on top of the solid blocks in front of the pistons that you're actually activating, because the glass blocks are just there to not activate this block. Technically you can also use slabs here as well, but I just use glass because it's solid blocks, it looks a bit nicer. So yeah, that's the reason I use glass on these bits, because they don't really need something like this. But yeah, now that we added our repeater, we should be getting one like that. If we activate them both, all the lines should be on. If all our lines over here are off, yep. Now let's actually just test these to make sure they work. So if I put the numbers 1111 into register A and register B, we should be getting all ones on the output. However, if we invert both the outputs, we should be getting all zeros. If I uninvert them, we're getting all ones again. And if we put the number 0000 into both registers, technically clearing them, then we should be getting no outputs when we don't have any inversion on. So that's the inversion bit done and tested as well. So now let's move on to the next part of the tutorial. Now comes the most complex part of this ALU, and that is building the actual half adders over here. And once we've done that, the rest of it is relatively simple until we come to the programming, because that's always fun to do. But yeah, so, well, let's just really get started. So the first thing we're going to want to do is over here, as you can see, we go up from the adders and down a bit. The reason we do this is because we don't want it looking wonky like this one over here. This was the first time I built it. It just was kind of wonky, and it saves a few blocks in the height factor and just adds only like 1 or 2 in the width. So that's why we go up from this and come down 2 blocks like that. So let's get started over here. We're going to want, as you can see, I've actually done it over here. But what we're going to want to do is from the inverters, we're going to want to go down 1 block, down another block like this, and up a block like that. And we're going to want to copy this pattern for all of these like this. So the way I'll just do this is I'm going to block along like this. And once I've done this, we're going to place redstone on just these 2 ones. We don't want redstone here. I'll show you why. Oops. And we'll break any block in the middle like this. So first of all, I'm just going to break the ones in the middle first. So redstone along these. And this is where we actually build the first set of half adders or XOR gates. So the way we're going to do this is, I'll just do 1 for now, and then I'll copy the rest out for the others. So we're going to want to go 2 blocks out like this, torches like this, block in the middle like that, redstone dust on top. We're going to want to block up on both of these torches again. And normally you'd just put a redstone torch like this in the middle, but since we're going to need carries for this ALU, we're going to go another block up, and we'll just put redstone torches like this. And then redstone dust like this, and more redstone torches like that. So the way this will work is it has an AND gate going into here, so a redstone torch into here. And this would normally just output into these ones with a torch over here, but we'll just go up 1, so we have this extra output over here for a carry, and these torches will still output into these, as the AND gate will still also output into these, so it doesn't really matter too much. So now that we've done this, we're gonna I'll just copy it to all the rest, and then we can start work on the other set of adders. Oops, I placed torch there. Then we're going to have redstone dust like this, and then we don't want any blocks in the middle because these are still separate at the moment. Make sure you don't accidentally join these up over here. So we'll have blocks like this, blocks on top of these torches again, and we'll just do the same thing where we have dust in the middle over here like this, block up on each of them, and redstone torches like this. So now that we've done this, there's only one thing left to do, which is put the input for the second set. So since we're doing left to right for least significant to most significant on the left, so least significant is on the left, and we're gonna we're gonna want our carry go from left to right as well. So where we're gonna do this, block between these two torches, block down like that, block in front of that, and we're gonna make kind of like a Z shape like this, as you can see. So we're gonna wanna repeat this for all of them. And let me just do this real quick. And I'll show you why. We don't, make sure to not place them in between still, or else. So don't place them in between this. Do it every other one like this. So now we're just going to place redstone dust like this, and then we're going to want to start work on our second set of half adders. And the way we're going to do this is try and make it exactly in line with the first set. We'll just do the exact same thing like this. So block up from this, and our two sets of blocks like this. And let me just repeat this for all of them first. I accidentally broke a block here. And then I'll just make this for all of them. There is only one difference we're going to do on this set, and we'll do the, instead of doing this, we'll just do a normal OR gate because we don't actually need this extra input over here. I mean, yeah, an AND gate, I think. We not an OR gate, but yeah. So blocks like this, redstone dust on these, and we still need our blocks over here because the redstone torch transmits to this block, which will transmit to the redstone dust. So we'll still need these blocks on top like this. And then instead of going up like that, we'll just place a redstone torch like here because it'll just do the exact same thing, and we don't need the extra output coming from here or input. Yeah, I don't know what to call it. And now that we've done this, we have a set of XOR, we have two sets of half adders over here. Now we're actually going to want to join them up to make a full adder, and the way we're going to do this is by making a carry. So since we're going from left to right, we're going to want to place blocks on top like this of these ones over here. And also we're going to want to place redstone torches on the right block over here. So if you're going the other way, instead of going this way, you'd go like this, and your torches, instead of being here, they'd be here. But since we're not doing that, we will be going this way from left to right. We're going to want our torches here like this. So the next thing we're going to do, so as you can see, if we have dust like this, they'll both go into our carry. So the next thing we're going to want to do is come down like this and have a block like that. And we'll have two blocks like this, and we're going to do this on every single section like this. So two blocks like this one too, and this one too. So now that we've got this, we're going to want to do the last bit, which is actually add the carry into the second half adder. And the way we're going to do that is by going like this, and a piece of redstone like this. And we'll just do this for each of them. So as you can see, I left that block earlier just so I could place this easier. Oops, where did I place that? Right here. There we go. So now that we've got this, as you can see, these are still in place. We're going to want to run a redstone line down this middle section. And since we're going from left to right, we're going to want to get a block and block over here where these join like this. So like this over here. And as you can see, that means this will be our carry in, and this will be our carry out. So we can even go down like this. And we can put a lamp over here and label this carry out. Ooh, not carry but carry out. And as you can see, that means the carry won't continue down all the adders, it'll only go into the next adder, as you can see. So if the carry comes on either of these adders, it will go trigger the carry line, and it will go into the next adder over there. So that's basically it. That's the second set. Of course, let's just add this sign over here. So carry in, and a lever, and there we go. Then there's one last thing we're going to want to do, and that's to, on the ends, go down like this to make the outputs over here, and I'll show you what to do over there. So that's basically it. That's the adders done, and we'll give them a test in the end of the video, basically. So yeah, alright, next section. So now comes my favorite part, which is fixing the broken bit, or in this case, not putting the broken bit in. So, one of the problems with my ALU previously, I think I wasted about an hour and a half worth of video footage, as well as like 6 hours of designing progress and stuff, was that I completely forgot to add this critical feature over here, which is called cut adders. However, in this tutorial, of course, because this is new footage, I will not be missing this part. So let's actually start building this. So it's a bit complex on the way that I've done it, but I think I'll probably be able to execute it out properly. So let's begin. So over here, the first thing we're going to want to do, this will be a bit complex, is we're going to want to go block up like this and over like this. You know what, I really should have done the and first, but we can add that in a bit later. It doesn't matter. You know what? Let's just do that and now. So the thing we're going to do right now is we're going to add an and toggle in, and the way we're going to do that is by placing torches on this side. You can alternatively place them on that side, but I'll just place them on this side. It's easier. Technically, you can place 2 torches like that, but we'll just have one, as it'll do the same thing. Block over here, block on top like that. And that's basically almost it. We'll just do this for all of them like this. And so now we have the output from this gate over here, this AND gate. Well, it's technically a NAND gate because this is the AND gate part. This is the NAND gate. We invert it and we get the output from here. And then we can block along like this. But what we're going to do is place a redstone like this. We're going to want to go one across like this, and then one up over here, and like this. So we have this kind of shape like this. So reiterating, that's a block on top of this one, block here on top of this one. It won't interfere with this, so don't worry. Block up so we don't hit that torch, and block down like that. The other reason we do the block up is because we need to actually make a control line for this as well. However, since we're doing a block up, we can block this line from going across by just placing a block here. As you can see, if I activate this, it will not be activated with that block, but without it, it will. So the way we're going to put this block here is we'll just have some pistons. So if we go across like this, if we have a piston like here, then we can control it like this, as you can see. Make sure all the pistons are sticky pistons. So now we'll just repeat this for all of them, and it's quite simple. Just blocks down like that, block up. And yeah, over here, make sure to remove this block or it might break some things. Then we're gonna want redstone across like this. And we'll just bring a line across like this, where we will do our ALU things over here. And let me just break this, because oh wait, I've done them incorrect. Hang on. And then we have blocks in front of these, and I'm just going to extend it out one more so everything's in line like that. And there we go. So now when I activate this line over here, let me just bring it out a bit so it's all in line with these. This will be and when we activate it, it should activate all these pistons like that. Pretty simple. And that will block all these lines over here. So now we're going to want to feed this into this, and that's where the cut carry comes in. Cut carry? I meant to say the cut ALUs, or skip ALUs, or whatever you like to call it. So that's what we're building right now. So as you can see, we'll just go up like this on all of them. And once we've done this, we're going to want to have pistons on top of these. So as you can see, we're just going to use the same technique we've done here with the pistons blocking the redstone. Because if we have a block here, it will stop the redstone line from the ALU being output over here. Well, without the block, it will. So we're going to want to go up like this, have a piston, and as you can see, it will just go like this, and it'll block it. So we'll just leave it over here for now. And we're just gonna go across like this, all of them, and we'll just place pistons in between, like this. And of course we're kind of running low on space over here. So let me just see how far everything else goes up over here. So we won't be able to have redstone across like this. We're instead going to have break these blocks first. We're going to have the line for the pistons going along here. However, you may have seen a slight issue with the torch going here, and we're just going to fix that by placing a non-solid block like glass or a stone slab on top of these torches like that, so the line won't interfere. Of course this line's going on, but we'll just place a block on all of these redstone just to make sure it doesn't interfere like this. So now if we run this out, if I activate this, it'll just activate the piston, and it will not interfere with this torch or this gate at all. And the same as any of these lines, if this piston is, if this torch is on, for instance, it will not transmit through to here. So we're just going to repeat this on all of them. So if I just block across like this, and let me just line it up right there. Then of course on any of them with the piston, we'll have the glass block. And as you can see, there's the torch underneath not going in. And then we can just have our line going like that. So when we activate this, it will cut the ALU. Of course, we're going to need blocks here like this to do that fully. And there we go. That's the cut ALU part. So, for the rest of the AND part, that's going to be a slight bit trickier. And let me just go look at the design real quick. So over here, as you can see, from the AND gate, since we invert it once, and we're going to need to invert it at the end, we'll invert it again over the pistons, and it's just going to go down into the output inverter, as well as this over here. So let's just build that real quick. So for the rest of the AND, we're going to want to, I guess we could just have a block here like this, join these up like that, run redstone across. As you can see, these join up, but we'll fix that in a minute. And then we're going to want to block up like this, and then I've forgotten how I've done it. I think I just, oh yeah, that's how I did it. Block up like this on top of this block, so stopping these blocks from joining. So this will not interfere with this, and vice versa. And then we're going to want to have a glass block on top of the piston. And that's so the AND line will not accidentally activate the piston. Because if we had a block here and redstone like this, it would accidentally activate. And we don't want that happening, so we'll have a glass block here. Then we need to invert this because we're going to invert it again. So we'll just have redstone torches like this. Now I probably could have done a thing where we didn't need to invert it by pulling this straight into here, but the reason I didn't do that is because this control line is already quite well taller than the others, and we want to keep it as small as possible. So it adds a tick, but it also makes it smaller. So now that we've done this, we're going to want to place more glass blocks down like this. And this is the thing where Java definitely cannot, will definitely not work, because as you can see, the redstone can go down, but still not activate the piston. Whereas slabs would not be able to do that, and solid blocks would activate the piston. So that's why we use glass like this. Oops, not solid glass. And so we'll just have it down like this. And now that we've done this, there's only one more thing to do. That's place a solid block down like that, redstone on top, and we'll just do that on each of them, like this. Solid block with redstone, and then we'll also add redstone torches in between like this. So as you can see, I went up like this, and not only for these pistons to activate it, let's just remember to add the sign. So this is cut ALU, not cut ALU, it's cut the adders, like that. But also, the reason we go up a block is so this redstone torch can hit this block over here. So we'll just do that for each of them like this. And now, that's basically almost it. There's only 2 more things to do, and we'll do that in the next cut. So see you in a minute. So now that we've built most of the ALU, there's only several bits we need left. We need to make the cut carry line, and this is quite useful if you're doing operations like XOR, because where you don't need the carry. And we also need to build these 2 bits over here, which is invert the output for certain things, as well as the ALU out. Technically you don't need this one, but it's quite useful if you want to have the ALU being able to toggle the output or not. So if you, this is because since the ALU does not give the output all at once, it'll, whenever you put the numbers in, it'll be flickering around constantly until it reaches the final output. You're going to want to have this line because you're going to want to have, you're going to put 2 numbers, wait a bit until it's finally settled, then get the output. Because if you have random numbers flickering in and out, and you accidentally save that to RAM, you can see where the problem is. So you'd normally have this on like a delay of however long the ALU takes to compute the operation. Well, the longest operation, basically. So that means it'll work for everything. So let's go and start making them. So the first thing we're going to want to do is we're going to build the cut carry, and this is quite simple. All we have to do is wherever we've placed a block over here for the carry line, as you can see, we're going to want to place another block in front of it like this. And we're going to do this for all of them, even including this one over here. So the block would normally be here, but we'll place it there. And on the first one, we don't actually need it because it doesn't count anything. But once we've done this, we're going to want to go up a bunch like this and place a sticky piston down like this. So that means when this piston is activated, it can tell that block to go down or not. So we're going to repeat the thing for all of these, and I'm just going to go up like this and around like this, so we mined out this block so it doesn't interfere. And we're just going to do this for each of them like this, and pistons like this. And so now when we activate it, let's just put redstone down first. Let me just make sure it's in line with everything else. This will be called cut carry. When we activate this, it should activate all of these. This last one's not activating, but we can put a repeater here. That will even cut the carry, the carry out, and we don't need to cut the carry in, because technically you could do if you need that cut out, but just don't put a carry in basically if you want to cut the carry. Now that we've done this, yeah, as you can see, they're all activated, which means it's technically, as you can see, the carry is being cut at the moment. And when we deactivate it, the carry from the carry from the half adders will be able to go into the next set of half adders, as you can see. So that's just that bit. Now the last bits we're going to want to do is just the last bits over there. So on the end, we're going to go up a block, another block like this. As you can see, they almost interfere, but it doesn't matter. Torch here, block out like that, repeater, block on top of that, repeater, make sure it's on 1 tick, repeater there, block up again, and there we go. And we'll just repeat this for all of them real quick. So let me just do that real quick over here. And we're going to break the unnecessary blocks. Repeaters on 1 tick. Block up. Like that. Torches. And then we'll just do the last bits over here. So I'm going to place blocks off the repeaters. Ooh. And more repeaters like this. Blocks off of these. and block up like this. And then we'll just put redstone down like this. And we're going to want to, of course, make the activation bit, which will just be a sticky piston like this. And so when we activate this piston, it will invert it. And when we deactivate it, it won't invert it. It will just let it pass through. And then we'll just go across like this and then add the bits over here. So for this last bit that I'm adding, you don't need it, but if you want it, you can just include it, I guess. Let me just make sure these are all in line. But technically, you don't need it at all. It's just for what I was saying earlier. So this will be invert output. We'll have a lever like this. If we activate it, they should all activate. Nice. And now we're gonna go across like this. And of course we could use the same old slab trick by going up a slab, or doing like this where it goes up one and blocking it like that. We could even go down one and have a block over here. But since this isn't essential, I'm just gonna have a repeater over here going through the block, and we'll just have this exact same line over here. This isn't essential at all. This is only if your ALU design actually needs this. I think only a few of my computer designs actually use a line like this, but it's just kind of like a thing if you need. So this will be ALU out. Spell out well. I spelled it wrong again. Out. Finally. And then just pistons like this. And of course we have to make sure to place all the blocks in like this. Once we've done this, just run across like that, and I'm pretty sure it's finished. I'm gonna say that pretty sure because I might have to add another section in where I've forgotten a part, and yeah, so sorry about that if I do. But yeah, now that it's finished, we're going to go through and test every different component again, make sure everything works as well as works together, and then I will show you how to program it. If you've already tested yours or just like you're confident that it's all working, then feel free to like skip to the next section where I show how to actually wire this up and like all the operations. So yeah, alright, see you in the next section. So this next section will basically be going over how to actually test it, and the way we're going to do that is, first of all, we're going to test from this side, and we're just going to test all these different bits going from this side to this side. So let's just test these registers over here. I think we've already tested them, but we'll just test them again to make sure. So first of all, we're going to set all the inputs as 0, do A, do B, and then as you can see, all the outputs should be 0. Perfect. So now if we do all the inputs as 1 and just do A and do B, all the outputs should be 1. As you can see, we can read them from here, this block over here. So yeah, they are all 1, which means this works. Now we'll just leave them 1 for now. We're going to do, so they should still remain 1 even if we put a 0 in here, because we're not resetting them at all. As you can see, they retain their state. So if we turn all of these off, they should retain their state as 1. Which is perfect. If one of them went 0, you might be like missing a redstone torch here or something. So now that we've done that, we'll try the inversion. So all the inversions should be outputting 1 at the moment. But if we invert them both, they should be outputting 0 at the moment. Perfect. So now, if we turn them off, if we input the number 0, 0, 0, 0 into both registers, we should be getting the same thing on the output of the inverters, and if we invert them both, we should be getting full 1s. Perfect. So now that we've done that, we're going to want to do, we'll do the AND gate first, then we'll do XORing, and then we'll do adding afterwards, and we can also test out the inversion. So at the moment, let's just test out the inversion first. So if they're all on, we should be getting a constant output like this, so they're all on down here. So now if we, as you can see, getting all ones from the out of the inverter, with them all ones going in. If we invert it, they should all be 0. Perfect. And then we of course we can read it from here. Oops, that's meant to be on 1 tick. I'm gonna put redstone lamps up like this, just because it looks nice. Oops. So this is 1, 2, 4, 8, and our carry out over here is 16. So there we go. Now we'll just we've tried this bit and we've tried this bit, so they work fine. Oops. Now let's just try the rest of these 4 levers over here. So first of all, we're going to try out and the way we're going to do this is we're going to put 0, 0 in the first one. So A and B on the first one are going to be 0 and 0. So let me just set them. Then on the second gate over here, we're going to want 1, 0. So this will be 1, 0, and this will be 0, 1, and this will be 1, 1. And the way we're going to do that is just, so this is both 0, 0, and this is both 1, 1. And we're going to have 1 on A over here. So the first number we're going to want to input into register A is 0, 1, 0, 1. So if we input that into A, then we're going to swap this one around to here for inputting into B. So there we go. And now, if we turn off the inversion, as you can see, 0, 0, 1, 0, 0, 1, 1, 1. Perfect. Now we're going to want to AND it, and when we also AND it, we're going to want to cut the adders. Technically, you'd also cut the carry too, but seeing as we're just completely bypassing the adders completely, we don't need to bother with that because it's going to be cut anyway. So as we can see, we should be getting an output down here. So the only output we should have on is this one, which is not turning on. And that is because I've turned these off. Ah yes, here's one of the problems we found just by testing. So I forgot to invert this. You will need to invert the AND by placing a redstone torch like that. It should be inverted. So when you turn it off, it's off, and when you turn it on, it's on. So that's why you bug test things like that, because even like just a little thing like that can break the whole thing. Earlier in the testing, you might have been wondering why your one might have been a bit different over here. That might be because you remembered to place this torch. But yeah, I didn't, so it was already using the AND gate because they were all on. It gave all on outputs. So now that we're doing this, we should be getting 0, 0, 0, 1, so 0, because 0 and 0 equals 0. 1 and 0 equals 0, if I can get through. 0 and 1 equals 0, and 1 and 1 equals 1. And we may also get a carry out, but that's why I said you can, of course, cut the carry if you want. You don't need it at all. But now that we've done that, yeah, I might just include the cut carry because it's a quality of life feature. So now that we've done that, I'm just going to deactivate everything. And the next thing we're going to want to do is try XORing the numbers. So we're going to keep the same numbers in. So 0, 0, 1, 0, 0, 1, and 1, 1. Because that's the 4 different states that 2 numbers can be in. And it is perfect that this is 4 bits because it also represents 4 states, this ALU. So first of all, to put an XOR in, we're going to want to activate the cut carry, and yeah, that's about it. Yeah, if we want to do XOR, we just activate the cut carry because the ALU pass-through is already going to happen. So 0 and 0 should equal 0. 1 and 0 should equal 1. 0 and 1 should equal 1. Perfect. And 1 and 1 should equal 0. Perfect. And then we, of course, we're cutting in the carry, so we won't have an output on that. So there we go. We've basically tested the AND and the XOR. We can also do an OR, but since these are both working, that means the OR gate will also work, and we'll program that in later. There's no like hardware solution. It's all just going to be programmed in. So let me just deactivate everything. Now let's just try the carry in. Yep, the carry in works. and cut adders, should just cut all the adders as we can see. So there we go, we've tested everything. Well yeah, I guess now onto the next section of actually programming this and, well yeah, making it work basically, and showing how to use it in your computer. So yeah, on to the next section. So now we're actually going to be programming this ALU. There's only one thing I forgot to test in the last section, which is actually using the sum. And the way we do this is we just leave everything off like this, and we're going to input the number 1111 into both A and B, and this is so we can check all the carries work. So that means the only number we should be getting 0, 1, 1, 1, and 1 on the output. Perfect. So that means the carries all work. So as we can see, if we put a carry in, we should be getting 1, 1, 1, 1, and 1. This is just a basic test to make sure all the carries work. Since 1 is going in both A and B, that means it'll just carry over into the next one. And this also tests that all the adders also works, because it tests that the actual adder can input a number and also the carry can input a number. And as you can see, it just works perfectly like this. So of course you can try a few different numbers if you really wanted to, but this is a good enough test for this. Now onto the annoying part, which is programming this ALU. In the first part of this, I'll just basically bring out all these lines and build the basic thing, and in the second part of this clip I'll just actually program it for all the different things you can do. So first of all, what we're going to do is we're just going to make a line where basically the middle of these are, and I'm going to do it around this section. And the reason we're doing this is because we're going to need to feed these all in and have a control line controlling them all. And if you do it in the middle, roughly, it can fit all of them, where if you did it like on the very bottom, then you'd have to bring these down, or on the very top you'd have to bring them all up. So the rough middle, like over here in line with these, is a good start. And just to make sure we've got everything right, if we go over to the tallest one, we should be able to let's just break all these blocks underneath them with the signs. I think I'm going to really regret this, as I forget what everything is. This is not going to be good. But now that we've done this, we can go down from the very tallest one, since actually this one's technically the tallest one, because it has the block up here, where that one's just redstone torch, so the input can be inputted on this level. Actually, so can this one. So if we go down from here, I think we might need a repeater here, because we were inputting into this one. We're going to want to go down one, and we're going to want to make it in line with this line over here. So as you can see, yeah, that's basically in line, and we're going to do this with all of them. So if we go across like this, that's in line, across like this, across like this, that's all in line with this over here. And these are going to have to be like this, and down like that, because we don't want the redstone going right into the torch. We want it being able to activate the torch. So there we go. So now that we have these lines, we're going to want to do the rest on the rest of them. So over here, it's already in line, so we can go across like this. And you may even want to bring these, route them around closer, which I think I might just be able to do here. Let's see. Oh wait, no, I have this one over here as well. This line over here. So let me just bring it up like this. And I think I can bring it one back by doing this. And just to save space is basically what you want to be doing with all of this. You want it being as small as possible so it doesn't take up too much room without like sacrificing in speed. So now the only things I need to do is this one over here, and yeah, I think that's the only one. So since it's interfering, these lines are right next to each other, I'll just do it down along here. So the way I'm going to do this is bring a line of it like this, and then we could just go up like this, and barely missed it, but we can just go like this. So there we go. Now that we have all these lines in line, we're going to be extending them out like this. And technically, you can extend this as far as possible. We'll worry about signal strength later. We can factor that in later. And then, I'll show you why we extend them out. Because we're going to want to be... you know what, I might actually just route these next to them. It'll make everything a bit smaller. There we go. There's one. And here's the second one over here. So yeah, just to save a bit of space, that's why I've done that. It's not going to affect anything, I don't think. So as we can see, then we have these lines like this. Hopefully I did not hit anything down there. And then these lines can be routed closer, I guess. Like this. And no, I'm gonna go. I'll just leave these lines like this. It doesn't matter too much. It's just because it'll get a bit slower the longer it is. I mean, the wider these are apart, it'll be a bit slower because you have to add more repeaters to reach all of them. But that doesn't really matter too much on this, as it's just really a concept video. And I'm not actually using this ALU in any of my computers at the moment. So now that we've got these lines like this, we're gonna for every operation we're going to want to do on this, we're going to want to add a line on top like this. So this over here is one operation. So this might be sum or a minus b or b minus a or whatever. And we're just going to do this for each of them. So the way we're going to do this is actually, first of all, we'll write a list of all the operations we want. So over here, I think I included a list over here. So and or not sum, subtract, and XOR. And let's just redo this a bit. So instead of subtract, we'll do a minus b, and we'll also do b minus a because that's always useful. XOR, and of course you can do XNOR or NOR or NAND if you want by just inverting the output at the end. So that's 1, 2, 3, 4, 5, 6, 7, and then say we could also add the carry in as just a separate flag. Would that work? Let's try and think. No, that would just technically be +1, I guess. No, I'm not sure we'd be able to do that. So we just have these simple ones over here. So and or not a minus b, I mean a plus b, a minus b, b minus a, and XOR. And of course you can do NAND, NOR, NOT, and all that stuff as well. But we'll just do those 7 things. So that means 7 lines. So 1, 2, 3, 4, 5, 6, and 7. So that's just 7 lines. Make sure these all extend out to this one over here. It doesn't need to be under this block, it just needs to be in front like this. And then we can worry about the signal strengths later once we actually program it, which will be the next section. So we'll just extend redstone across like this. Sorry if this is giving anyone nausea from the movements, but oh well. There we go. And then we'll just want to do extend these lines out like this. So there we go. And technically they don't need to extend to the really end, because you'll see why when we program it. They only need to go to the ones we want them. But this is just easier to do like this, extend them to the end. Because it means you can reprogram them if you really wanted to. So then we'll have lines across like this. And then we're going to start work actually programming it. So then we'll place redstone torches, inverting them all like this. And we'll have levers like this. You do have to have these torches here, because even though there may be torches here, and you can think, oh well, we just won't invert this line and leave this line, and not invert this line either. You cannot do that. You have to have these torches here, or else other ones will interfere with it and corrupt the signal. So now that we've done this, let's just add repeaters. Make sure the repeaters, as you can see over here, is on top, where we might have a torch here for actually programming this line. We don't want that, so we'll have a repeater behind it. And I'm just going to do this on every single one. Bit of lag stopping me from placing them. And as you can see, that just extends the rest. We only need one set of repeaters. So now that we've done this, we'll just program it, then we can add in the next set of repeaters. And yeah, alright, see you in the next clip. So now we're on the last section of actually making this thing. I mean, ALU. We're on the last section of making the ALU. And as you can see, it's gotten a bit large, even though it's just a 4-bit ALU. And that's mostly due to the encoder over here. And this is just the control circuitry. It just makes it a bit large. However, you can move this anywhere. You can move it across into distance, you can move it on top or below, as long as all these lines actually reach the right things with the correct signal strength. So now that we've actually done this, we're going to want to put repeaters in, and then these are just on-off things, like this. But we're going to program it, and I'll also show you how to encode it into binary if you don't want to have this many inputs on your computer. So first of all, we're actually just going to wire up the signal strength, make sure everything reaches everything. And the way we're going to do this is by placing torches on the very end one that you have, like this, on every single row, like that. So now we've done that, we're going to activate it, meaning that all these torches will turn on. And as you can see, we're going to need a lot of repeaters. So if we just place repeaters wherever we need them, like this. So this needs a repeater here. Make sure it doesn't like interfere with any of your components or anything. This one will need a repeater around here. So what I'm going to do is I think I might just be able to go like this. And we'll just wire it down like this, and then I'll make this a glass block instead. So then we can just go like this. The sneaky little cheat of using glass blocks. Actually, this can be a solid block, I think. And there we go. That just goes in like that. As you can see, I just used a glass block, so the signal will go into this block down here, and it can also pass backwards because I didn't really have enough space over here. Maybe I did, but I could have probably placed just a glass block over here, and that would have worked just as well. But oh no, I don't think I could have, because this. But this glass block will just let it go backwards like that, and yeah, that's just that bit done. Now let's work on to the other one. So just these bits. This bit activates that torch, so it's fine. This bit does not work, so let's just place some repeaters here. I know they go there because of these repeaters. And these bits get activated too. So that means all our things are activated. Now, I'm just going to turn this off, and we're going to break all these torches over here, because they're not actually needed. Some really delayed breaking action there. I really don't know why this world lags so much. It could be due to all of this stuff over here, but it's just a bit odd. I don't think it should lag like that. But seeing as I have pretty good hardware, definitely enough to run this. But now that we've done this, we can actually start programming it. So what we're going to want to do is actually designate what all of these are. So I typically like to designate the first one, the one that I'm going to use the most, as the first one along. Because technically, we don't actually use any repeaters in between. But if I was using loads and loads of functions, of course, I might have it wrap over, so it saves bit space. I would have like repeaters in between. That means the further out they are, the slower it's going to take for it to get to the ALU. Where this one, since it's right in line with the ALU, it'll be the first one that will work. So the function that I use the most is probably a sum, which is just a plus b. Then we're going to do a minus b, b minus a. So you can do either number, subtract each other. And normally you'd only really need one of these. However, Sometimes it is actually quite useful to have the opposite way over, because if you have one number still in the register and you only want to reset one register, that's why you'd use both of these ways around. Then for the rest of them, it doesn't really matter. We can just do and XOR or, and what was the last operator? Not. There we go. So this will work a bit different because it'll just not whatever number goes through. So it's a bit. I'll show you how you can hook that up. You can hit the NOT gate, whatever you want. You can make it so only it'll invert one of them, and you don't want any numbers in the second one. Or you could make it so it inverts both, like I'm gonna do, and just combines them anyway, as in kind of almost like an OR gate. So now that we've got our numbers in like this, I think we've done most of our operations. So 1, 2, 3, 4, 5, 6, 7, and then we've done all 7 over here. So now we're actually going to hook these up. So for summing, as we've said earlier, all we have to do is, I don't think we have to do anything. So the sum is complete, we don't need any torches whatsoever. For the A minus B, we're going to be using 2's complement, I think, so we'll need to do something over there. And the way we're going to do this is, hang on, let me check my notes, let me program these all in, and then I'll show you how to do them in a bit. I don't want to have to do this on the fly, accidentally breaking things. So yeah, let me just do this first. See you in a minute. So I noticed a very small mistake while making this, and that was I also hooked these lines up with these, which is the right A and right B for the A and B registers. And normally on most of my computers I just have these as separate things. And so what I'm going to do is I'm going to for now I will just leave them in and add 2 extra lines, but normally if I was going to make a computer, seeing as these normally need a lot of delay and repeaters, I'd just move all of these over here and just remove them completely. But seeing as this is just a tutorial video and timings don't really matter, I can just add these on the end like this. So this will be right A and this will be right B, and there we go. So let's just add these on like this, and these will need to go on there like this. And on your computer you can technically just leave these in, they don't matter too much. So right A is A, oops, A and B, and we could just destroy those bits like that. They're not needed like this. And hopefully this bit reaches. If it doesn't, I'll just have to add a repeater. I'm going to add repeaters here and here, and there we go. And actually for my timings I could just add more repeaters like this, and to make it take longer to activate. And that's what I'll probably do on my computers from going forward, and I'll show you how that works in a bit. So then, now I'm going to get back to actually programming it. Now that I've finished programming the ALU, there is only one thing left to do, which is show it to you. But before we do that, I just have one thing to say about this ALU, and that is the NOT function is, I kind of forgot to put some certain bits in it, and I have been trying to add them in, but it's just not really worked out without having to like break all of this and move it back a few blocks. So what I'll do is in another video I'll show you how to add a proper inversion function. I'll show you what that means as well in a minute. But this inversion function, the way it works is technically it's a NOR, so I'll just rename it that, because what it'll do is, I think I've got it programmed, so all it will do is just OR, and it will also invert the output. So because it won't just, so a proper inversion function would have a selection where you could either invert A or invert B, and the way you do that is you just invert the A line, but then you'd also cut the B line by just cutting it straight out. But the problem is I haven't really included enough space for me to build that. But I'll release another tutorial on how to include that if you really need it in your ALU. But seeing it's not really a thing you really need. The only reason you'd have a invert A or invert B line is because that also means you'd have the functionality to add one to A or add one to B, because it also means you could just cut A or B off and just add one to it. But yeah, so it's going to be missing those 4 functions, but I don't think they're too essential. The add one is kind of useful, but as I said, I'll do a tutorial fixing that problem later. In this video, I'm just going to go over these bits. So the first thing we're going to do is we're going to label the backs over here. And I like to do this because since we broke the signs earlier, it just means we know what to label. So as you can see, I've already labeled the first 2. So the first one is going to be register A, register B. Then we have these lines left, so invert A, invert B, and carry in, which technically is also +1. Then we have this line, which is the carry line, so we'll just put that in right now. And let me just go like this. So this is cut the carry. Then this line I think is bypass adders. And then these 2 lines is one of them's invert outputs, and the other one is ALU out. There we go. So now what we're going to want to do is actually start programming them in. And as you can see, I've already programmed them, so I'll just show you what they are really. So for to do the sum command on this ALU, all you need to do is on the furthest line, which is the ALU outline, put redstone torch on. And because the ALU is by default with no lines activated, except the last line of course to get an output, is set to sum. Also on every single line you're going to want to have one of these outputs anyway, because that's what you're going to do. Whenever you do an operation, it's also going to give the ALU out. And what's going to happen is you want to do your operation first, then give your ALU out. But seeing as you want that in the same CPU cycle, and you don't want them happening at the same time, all you have to do is just add a few repeaters like this, and set the repeaters to however long this ALU takes to compute. So for just good measure, I'm going to set this to, let's say 12 ticks for now. So say this ALU took 12 ticks to compute, I'd set the output to 12 ticks, plus the piston tick of course, because the piston is going to take 1 or 2 ticks to go down. So you could of course, if it takes 12 ticks, you'd set it on like 10 ticks because of the piston, or whatever. But I'll just set it to 12 ticks for now. And that means whenever I activate the line, it's going to do the operation, make sure it's fully done, so no like flickering lines or anything, then it will give the output. So let's just demonstrate by doing 1 + 1. And so if I put that in A and put that in B, as you can see, we are not getting an output yet. That's because we haven't chosen what operation we want to do. But then, as you can see, the answer's already been calculated. So whenever we choose the operation we want to do, it will recalculate the answer, because of course you might have other lines. Then after a while, after it's finished calculating, it will give an output. And this line is just to make sure it finishes calculating before giving an output, or as I've said already, it will just like corrupt the data maybe and mess up the RAM. So yeah, that's how that works basically. So let me just set both of these registers back to 0. Then the second thing we're going to have is A minus B and B minus A. So we'll do this one first. And the torches, I'll probably include like a list in the description, or a comment, or a pinned comment or something, going over where all these torches go. So for A minus B, we're going to want to have a torch on the invert, was that B? A minus B, yeah. So for A minus B, since we're doing 2's complement on this ALU, not 1's complement, you can do 1's complement, but 2's complement subtraction is typically better, because that also means this ALU can deal with negative numbers. However, if you want to do negative numbers on this, you might want to cut out the carry out line, because that wouldn't really make sense anymore. And negative numbers, of course, one of your bits is going to be the flag bit, so that means if you had a 4-bit ALU, it could only do 3-bit numbers. However, it could also do negative numbers. But yeah, that's just a downside of having negative numbers, because one of the bits is the signal bit, or to tell if it's positive or negative. So for A minus B, we want a torch on invert B. We also want a redstone torch on this over here, which is carry in +1. So to do 2's complement, of course, you invert one of the lines, and you also +1. And then the only other torch there is of course the one on the end, telling it to give an ALU out. Of course, if you didn't have this line whatsoever, you just wouldn't have these bits at all. So if you didn't have this, like I said earlier, you just wouldn't have these at all. Whoops. Then we're going to be doing the opposite for B minus A, and the only change from A minus B is instead of inverting the B line, we'll be inverting the A line. So we're going to have a torch on invert A, as you can see, because that's the number we're minusing. And then we're also going to have a torch on this line over here, which is the +1 line, and of course on the end like that. So the third operation we're going to be doing over here is and what we want is a torch on, of course, the and a flag. Then we want a torch on the cut carry flag. You don't really need that, but sometimes it will give out a carry, so yeah, you just have a cut carry just in case you're doing conditional branching and one of your carries is, and one of your conditions is that you have a carry. Yeah, you want to cut that just in case. Then what we're also going to want to do is this torch over here next to the cut carry, which is bypass the adders. We're going to need to do that. And then the last torch, of course, is just this one over here, which is for all of them. So then the next operation is XOR, and that's quite simple because it's basically sum, and all we need to do is cut the adders. That's all we do. So over here for the XOR, all we need to do is cut the carry like that. Not the adders, the carry I meant. Then the next operation is OR, and what we're going to do for that is over here, this line, which is we're going to do and we're also going to do cut the carry. And this means that it'll basically, wait, have I done that correct? Let me just check, because we have and over here. Ah yes, because for whenever we do OR, it's basically the same as and, right? But we're also going to cut the carry as well as not bypass the adders, I don't think. Because this is and we bypass the adders over here. And for OR, we don't bypass the adders, we just activate the cut carry flag as well as the and flag. And this means whenever we put in numbers, so let's go 0, 1, 1. So like this on A, and we'll do this on B to give us all the 4 possible states. And our output, whenever we do the OR operation, let's do the AND first. If we select AND, as you can see, 0, 0 equals 0, 1, 0 equals 0, 0, 1 equals 0, and 1, 1 equals 1. And now let's do the OR command, which is basically an inverted AND command, kind of. So as you can see, 0 and 0 will equal 0. So it's not fully inverted, but you can see what I mean, where it's everything's inverted except this one, and wait, it's not really inverted, but you get what I mean. So 0, 0 equals 0, 1 and 0 equals 1, 0 and 1 equals 1, and 1 and 1 equals 1, like that. So even if we did say 1, 1, 1, 1 plus 1, 1, 1, 1, it should still come out with 1, 1, 1, 1, even though the carry's been cut and everything. There you go. Perfect. So that means all works. So now the next line we're going to want to program is NOR, which is basically the NOT, and all we have to do extra to the NOR line. So we're going to activate the AND line, we're going to activate the cut carry line, and the only thing different we're going to do is activate the invert output line, as of course in this as well. So that means it will basically do the same as the OR, just invert the outputs. So unfortunately we don't have NOT on it, but I'll show you in a different tutorial how to do that. So as you can see, 1111 plus 1111 is 0000 on a NOR. And if we put all the different states in, so 00 like this into A, it doesn't matter if this is still on because these are kind of separate things. And then 0010 01 and 11 into B. Then we should get yeah. So this is just the inverted way. So the only number that turns on is 0. So perfect. Yeah, that's basically everything programmed in. And if you didn't really get what I was programming, of course the right A is going to be programmed into right A, and right B will be programmed into right B. These don't really need to be included in these. I've just done it over here because it's easier. Then yeah, that's basically the entire tutorial done. There's only one more thing, which I'm not sure if I mentioned this, but yeah, we need the repeaters in here. I forgot to add them, so add these. There's one more thing that I need to mention, which is if you want these inputs over here to as you can see, they're all separate inputs at the moment, and say you didn't want that and you wanted it all as in just like a kind of binary input, because at the moment these are decimal. There it's either this one's on or this one's off, this one's on or this one's off. There's over here there's like 9 inputs, and if we want to reduce that down, what we can do is turn them into binary. So we could just toggle a binary input and that will just tell it what to do. So the way we can do this is let me see, I'll leave these ones separate for now. We'll just do these ones, and since there's 7 different inputs, that means there's 7 combinations, so we can use 3 bits. So what I'm going to do is I can just go like this, and we'll make a decoder over here. So I'll keep these signs down here. So let's just take these ones off real quick. And if I go down like this, actually I think I've done it a bit wrong. I'm going to need to go one in like this. So if I go like this, and I'll leave these ones separate for now. I'll show you what I can do with them in a minute. If we go like this and then just extend these lines out like this, we can create a simple decoder. There we go. So then what we're going to want to do is, let's come down from here. So this will be a bit, and then one here, and one here. And then we can come down from here like this, and extend these lines a lot. Now once we've done this, we're gonna put some levers on like this, and we can also label these 1, 2, and 4. I'm just making my compact version of the decoder. It means it'll be a bit slower than a normal decoder, but it doesn't matter in this case. It'll just be a bit more compact. So what we're going to do, we're going to want to place blocks all like this on every single one, in front of every single one like this. We don't need these blocks at the end for now. And once we've done this, I'm just going to break all the blocks underneath to save the space. And there's of course this block over here. Now that we've done this, we're going to have redstone. These ones will be repeaters, and we're just going to have alternating lines like this. So redstone, repeaters, redstone, and then of course repeaters here, redstone here, repeaters here, and redstone here. This is just a compact version of it, so that means of course you have all these added repeater delays, but of course you could make an extended version which will make it slightly bigger, but it will also mean you won't have like all these extra delays. So then what we're going to want to do is run redstone across like this to these torches on the end. We're going to want to break these torches too because we don't need them anymore. So once we've done that, we can just run redstone across like this. And then I'll just break these in the middle over here. Then we're going to want to, so since there's 7 different combinations, we're going to have 1, 2, 3, 4, 5, 6, and 7 like this. Well, there's technically 8 including 0, 0, 0, but we'll just leave that blank for now. So that means these should actually be inverted again. So what I'm going to do is, just to make it simple, I'm going to come down like this, and I'm going to place a block all like this, repeaters like this, on 2 ticks to stop any signal variation, because technically these decoders take 2 ticks to do. I still haven't finished them yet, but so we'll put these on 2 ticks and place blocks like this. And that means it should, it should reach the end like that. Then what we want to do is we're going to place redstone torches on all the blocks that don't have a torch on top. So we'll just do it for this one. So torch, block, torch, block, torch, block, and over here like this, and on this one over here like this. Then we'll place blocks on top of those torches like this. And I'm not actually sure if I've done a tutorial for these before, but all it is just making a very simple, I think they're called either like multiplexers or demultiplexers. I can't really remember. But yeah, that's it done. Then we'll just place redstone torches on the inside like this, on every one of these. So it's gonna take a bit of time to do them all. But once we've done them all, yeah, that's all of them. Now, as you can see, if we activate 1, 1 turns on. Activate 2, 2 turns on. 3, 3 turns on. 4, 4 turns on. 5, 5. 6, 6, and 7 will be 7. So there we go. And then you've just reduced 7 inputs into only 3 inputs. So yeah, that's why you do something like this, because then these 3 inputs can go right into your computer, and that just makes it a whole lot simpler. Why did I break these levers? I don't know why. And then of course you have these as well, which you're going to want to activate them separately because they're just the right to the registers. These are basically separate items. So there we go. Let's actually test a few operations out. So what I'm going to test first is I'm just going to do a simple addition of the number 3 and 5, which should equal 8. So if I put the number 3 in register A, actually no, I'll do 5 and 3. So 5 will be, that means I can do subtraction. So 5 will be in register A like that, and 3 will be in register B like this, and then these can remain on, it doesn't matter too much. And then what we're going to want to do first is, say I just want to add the 2 numbers. So let's trigger line 1, which is add, and as you can see 5 plus 3 equals 8. Say we want to do A minus B, so 5 minus 3, and so let's trigger number 2, which is that. We'll get the answer, which is 2. Perfect. And so how about we want to do the opposite way around? So we want to do 3 minus 5. We're going to trigger 3, and we get the answer as let me see, so negative 1, 2, 5, 3 minus, I think this is -2. -1, -2. Yeah, this is -2. Hang on, let me think. 3 minus 5 is -2. Yeah, this number is -2, and I'm pretty sure that's correct, because if they're all on, it's, yeah, because you plus the 1, so yeah, this is -2, basically. This bit is the, so this is negative, and this number is 2. So yeah, -2. And then let's do some other operations, like say and that's actually 4, isn't it? And if we AND the two numbers, 5 plus 3 is technically 1, because it's only, these are the only bits that are on both A and B. Then we can of course just do all the others just to make sure they all work. So 1, 2, 3, 4, 5, which is XOR. 5 plus 3 in binary and XORed is this. Yeah, that's correct. So yeah, you can see it basically works. Give it a test, see what you can do with it. You could probably put this in a calculator as well. Of course, you won't need some of the functions, like you only need addition and subtraction really on a calculator, and possibly the plus one, which I'll have in another video. But yeah, I guess I hope you liked this tutorial. Hope it helped a lot. But yeah, I guess thanks for watching. Please like and subscribe, and I'm out.